Good day, dear colleagues. Our training track is called Compressible Flow Simulations using quasi-gas dynamic equations in OpenFOAM version 2012. My colleague Andrew and I will give you a lecture where I am going to tell you about our quasi-gas or regularized equations, which are implemented into OpenFOAM as a calculating kernel QGDFoam, and tell about our task. And then Andrew tell you about QGDsolver, and together with you we'll have the calculation of the flow in the L-shaped channel. Version 2012 is on the site github.com uni-cfd lab. The main works of introduction of regularized equations into the open program complex OpenFOAM were carried out and are being carried out on the laboratory base open source software laboratory for digital modeling of technical systems in the Ivannikov Institute for System Programming of the Russian Academy of Sciences in Moscow. The main directions of the work are the following: development of software for solving problems of mechanics of continuous media, numerical simulations of industrial problems, and also education and consulting. This information you can find on site indicated at the end of the slide. Now, about the plan. The first, training course materials. The second, introduction into QGD equations. The third, the theoretical part about the equations themselves, about the choice of the parameter tau, about the initial and boundary conditions. The fourth, the practical part. Here we'll do the following way. At first, I'll give you a short review of the task which we are going to solve, and you will see the view of the result flow. And then Andrew will do everything together with you, and conclusions. Here I'd like to remind you what you need to fulfill the task. We have to have basic knowledge of OpenFOAM, to know basic commands for Linux terminal, and have pre-installed OpenFOAM version 2012 on your computer, or ability to boot from USB. In this way, we will download our version, install it, and load our work case. Besides, in the folder materials, we can see the presentation and the results of the numerical simulation as films. And in the folder cases, you'll find our training task. In our training track, we will have a look at the basic principles of work of QGDFoam solver, consider setting an initial and boundary conditions for our task, and start our program. What is a quasi-gas dynamic equation? QGD system, or the system of quasi-gas dynamic equations, has been developing for more than 30 years. And it's appeared in the process of investigation performed by a small group of scientific research workers of the Cardiff Institute of Applied Mathematics of the Russian Academy of Sciences in 1980s by Professor Boris Четверушкин, together with Tatiana Yelizarova. When she entered the studies in the beginning, she immediately wrote the first variant of quasi-gas dynamic or regularized equations. These equations differ from classical gas dynamic equations by additional terms, which have the form of the second special derivatives. The new model allowed to construct effective algorithms for solving the area equations and then for the Navier-Stokes equations. Later, the quasi-equations were represented in the form of conservation laws, were studied in details and were theoretically justified by Professor Yuri Sheretov. And moreover, he constructed a quasi-hydrodynamic system contiguous to these equations. The principal and essential distinction of the QGD approach from the Navier-Stokes theory is the use of the spatial time averaging procedure for the definition of the main gas dynamic quantities: density, velocity, and temperature. The additional smoothing with respect to time is the cause of appearance of additional dissipative summands in the equations, by which the QGD systems formally differ from the Navier-Stokes system. The influence of additional terms is inessential for the stationary and quasi-stationary flows for small Knudsen numbers. However, for strongly non-stationary flows and also for the Knudsen numbers close to unity, their contribution becomes essential. Precisely in these classes, you can find the advantages of the models. The additional terms manifest themselves as effective regularizers or smoothing terms. About advantages and disadvantages. QGD algorithms work without flux limiter, work at high Reynolds numbers without TVD schemes, converge monotonically to real solution, don't involve Riemann solvers, and work without any correctors. The procedure of approximation is universal for all types of flows. And about drawbacks, we have a slower calculation, additional conditions for stability criteria, and we must have finer grids and smaller time steps. QGDFoam can be useful for uniform flow simulations in the wide range of Mach numbers, from subsonic to high velocity supersonic flows, and for scientists to solve complex set of equations. To bring the computational framework alternative to piezo simple, and for researchers or engineers for different tasks. Differences from other solvers are in ranges of Mach numbers. QGDsolver differs from raw center form, lower Mach boundary, from raw pimple form, upper Mach boundary, from pimple center form. QGDFoam differs the use homogeneous approximation for all Mach numbers. Each solver implementing QGD algorithms use libQGD library. And two foundation solvers, QGDFoam and QGDFoam, show essential principles of QGD algorithms. QGDFoam is for all Mach numbers, compressible viscous flow of perfect gas. QGDFoam is for incompressible viscous flow with buoyancy. And other solvers are the combination of foundation algorithms and OpenFOAM models, which are for flows with particles, multi-phase flows, and transport phenomena. How it works? QGDFoam governing equations. Here we see our QGD system of the Navier-Stokes equations. In general, these equations can be obtained in different ways. For the first time, QGD equations were constructed on the basis of a kinetic model involving free molecular motion and Maxwellization. Later, using a different scheme for the Boltzmann equation, and later using conservation laws written for a small stationary volume of gas. But all these methods for constructing the QGD equations are not rigorous. But QHD equations were rigorously derived as based on the classical postulates of fluid dynamics. An analysis shows that QGD and Navier-Stokes equations are closely interrelated and don't contradict each other. But the most simple method is based on averaging or smoothing of the classical Navier-Stokes equations over a short time interval. Because to get smoothing system, it's necessary to average equations over small interval tau, to substitute average values with instant values, to substitute time derivative terms using original equations, and to neglect of second time derivatives to drop out small terms proportional tau in square and terms that are proportional to viscosity and proportional to product of tau and viscosity. As a result, the smoothed system differ from the Navier-Stokes system by additional dissipative terms, proportional parameter tau. The smoothed system gas dynamic equations comprise continuity equation, momentum equation, and energy equation with a regularized mass flux Gm, regularized stress tensor P, and regularized heat flux Q, where P&S and QNS are classical Navier-Stokes viscous stress tensor and heat flux. We have a perfect gas and specific internal energy U. Universal gas constant with tilde equals universal gas constant derived molar mass. And our additives are indicated in red. Tau have the time dimension, and when parameter tau tends to 0, QGD system of equations reduces to Navier-Stokes system. These regularized equations are approximated using entropy preserving schemes. And regularization terms are calculated in half points. Regularization terms in OpenFOAM on phase centers can be calculated in two ways. The first, by approximating fluxes at phase centers and interpolating flux divergence at cell centers to phase centers. The second way, by using finite difference methods to calculate partial derivatives. The regularization parameter tau must be selected to be equal less than some characteristic time. For rarefied flows, tau is a mean time between collisions, which equals mu divided by pressure multiplied Schmidt number. For dense flows, additional numerical dissipation can be chosen as tau, which equals alpha multiplied computational grid step divided by sound speed, or the same plus viscosity coefficient divided by pressure multiplied Schmidt number. The next expression is the dependence for the dynamical viscosity coefficient mu from the temperature. And for flows with shocks, we need more dissipation. Viscosity coefficient must be replaced by mu QGD plus mu. The value of mu QGD is derived from tau by analogy to rarefied flows. Mu QGD equals tau pressure Schmidt QGD, where Schmidt QGD is a constant in a range from 0 to 1. We also need the heat conductivity coefficient kappa, depending on Prandtl number and gamma. And the time step is selected according to the current condition. Delta time should be less than some coefficient multiplied tau. And this coefficient is usually 1.5. And in our case, this condition is determined by the parameters max current and max delta T in control dict. We are in this slide considering the following types of boundary equations for the supersonic problem: wall, inlet and outlet. And mathematical description of these boundary conditions are set out on next slide. Here we see boundary conditions for the velocity, temperature and pressure. For the velocity, it's the condition of slip and no slip. The product of n and un equals 0, and u tau derive in normal direction in the first case, and the velocity equals 0 on all components in the second. Adiabatic and isothermal conditions for the temperature are zero gradient and fixed value. In the first case, the temperature derivative in normal direction equals 0. In the second, the temperature equals inlet temperature. And pressure, and about pressure conditions. It's necessary that the mass flux Gm on the wall equals 0. To get these on the assumption of the velocity in normal direction by n, or the velocity equals 0, and the pressure derivative in normal direction must be equal 0. To do this, we put QGD flux or zero gradient, that is the derivative of pressure in normal direction, equals 0. Inlet boundary conditions for supersonic flow are fixed pressure, temperature, and velocity on inflow. For outlet, we set soft boundary conditions for supersonic outlet, zero derivative in normal direction for pressure, temperature, and velocity. Summarizing what is said above, let's name the keywords in OpenFOAM: slip, no slip that fixes the velocity to 0 at walls, fixed value, similar no slip, zero gradient, applies a zero gradient in normal direction condition, QGD flux, and the total pressure condition. And to do one-dimensional and two-dimensional calculations, it's necessary to use an empty condition. To apply this condition, it's necessary for patches whose normal is aligned to geometric directions which are not involved in simulation. How to set up case? To install our version 2012, it's necessary to download QGDsolver according to this reference or using git clone. When you download QGDsolver with Andrew, it will be necessary to compile it using alphaQGD script. QGDFoam case consists of folders 0, constant, and system. In our case, in the folder 0, there are files to determine the pressure, velocity, temperature, alpha coefficient, and the Schmidt number. Gas properties are described in the dictionary thermophysical properties. And on default, turbulence mode is switched off. Numerical schemes settings are stored in favor schemes and favor solution dictionary. Time advanced control is in control dict dictionary. Mesh is in block mesh dict dictionary. Decompose par dict dictionary is for parallel calculation. And to start and solve our task, we have to prepare a case folder, to make a grid, to determine initial and boundary conditions, to specify physical gas properties, to choose regularization parameter tau, to determine time settings, and numerical schemes settings. Let's go forward to our flow in L-shaped channel. Our case L channel has the task about the flow in the L-shaped channel. On the right, you can see the image from the physical experiment where you can see the density gradient, or so-called Schlieren image. And on the left, you can see the scheme of the computational domain and its sizes 1, 1, 1.5, 1, 2.5, and 2. Gas flows upwards, spreads between the walls, goes to the upper wall, is reflected from it and goes to the right. The problem is solved for air under normal conditions. And we set density, temperature, and sound speed are equal to unity at 1. And then pressure is equal to universal gas constant with tilde. Here we can see the scheme of the computational domain. The beginning of the coordinate system is between points 0 and 3. Axis X is directed to the right, axis Y is directed upwards, and axis Z is directed in our direction from point 3 to point 1. To start the prepared mesh, you can with the help of common block mesh. To specify the computational domain in the folder system, in the dictionary block mesh dict, you have to give the coordinates of the appropriate vertices. For example, point 0 has coordinate 0 in x direction and 0 and y direction, and for instance 0.04 in z direction. The area is dimensional. Everything is calculated in meters, so we said convert to meters equals 1. Now, in this slide, we describe 3 calculated blocks with the help of hex cells and uniform grid. The first block has 50 cells in x direction, 50 cells in y direction, and 1 cell in z direction. Having all these, we move anti-clockwise beginning from the back surface when we specify numbers of vertices. And then we have to determine boundaries. In flow is described with patch number 3, for example, 3, 2, 1, 0 on faces. Similar to that, outflow and walls are described in a similar way. Also, we have to describe the boundaries sides which are charged with the type empty that is necessary for the third fictitious direction. For example, we can point boundary condition for the pressure on the wall and the velocity for the inflow. For the pressure, we use type 0 gradient. For the velocity, we use type fixed value. Uniform value is 1.2 only in the y direction. Now, we will consider initial and boundary conditions of our task about the flow in L-shaped channel. These conditions will be given in the appropriate dictionaries of the folder 0. At the initial moment of time, the velocity inside the computational domain equals 0. The pressure is 0.7242 pascals. The temperature is 1 Kelvin. For the inflow, we give fixed the same temperature and pressure, and velocity is 1.2 in the y direction, which is directed upward. And the parameters of our task are so selected that 1.2 is the equivalent of the Mach number. Dictionary alphaQGD in folder 0 looks like this. As alpha is the tuning parameter of the numerical QGD algorithm, is a coefficient, the dimensions are 0 everywhere. Inside the domain, alpha is 0.5. For the inlet, outlet, and walls, values are taken from the internal field. Also, we will consider the dictionary for the Schmidt number. As the Schmidt number is also non-dimensional, we have 0 everywhere. Inside the field, it equals 1, and on the walls, it equals 0. The next. Let's consider the file for the velocity in folder 0. The dimension is 1 meter a second. Inside the field, the velocity equals 0. For inflow, the velocity equals 1.2 in y direction. For inflow, 0 gradient. On the walls, we have the condition of slip. about thermophysical properties. All solvers use thermophysical properties libraries, and HEAP C QGD therma are used instead of HEAP C therma only. And for thermophysical properties, we have the following. Molar mass equals 11,640.3. The problem is solved for air under normal conditions, and for our calculation, we take density, temperature, and speed of sound equal unity, and we obtain specific heat capacity at constant pressure equals to 0.5. Reference temperature have to be there in version 2012. And physical viscosity equals 0, and Prandtl number is approximately 0.7. QGD regularization parameters are set in subdictionary QGD of thermophysical dictionary. Implicit diffusion we specify as true, and we have to choose calculating model of viscosity summons. We choose the model const Schmidt-Prandtl model 1, which QGD used by default, and inside model 1 we set up both Schmidt number and Prandtl number equal 1. We chose model 1, where parameter tau is calculated as the coefficient alpha multiplied by computational grid step derived by the sound speed. Diffusion terms can be approximated with implicit or explicit scheme. The trigger is located in the thermophysical property dictionary. And now, let's specify the following parameters in the dictionary contradict. Start time of calculations 0, end time of calculations 4.5, start time step interval 10 in degree minus 8, right interval 0.1, max current 0.2, parameter right control is specified as adjustable runtime. That means we have to adjust the time steps to coincide with the right interval. Then the parameter adjust time step we specify as yes. It means that we adjust the time step during the simulation, and current number we specify as maximum 0.2. Approximation schemes for tau terms is set in the Fourier C subdictionary of Fourier schemes dictionary. And there we use only central difference schemes. The specification of the linear equation solvers and tolerances are made in the Fourier solution dictionary. So you will see how your calculation goes on your screen. And your calculation will look like this. On this slide, you see the result of your calculation, which will look like this. And on the slide, the results of calculation on inflow that equals 1.2 are represented. On the left, the result from time 1.3 and on the right for time 2. Coefficient alpha is equal 0.5. Parameter tau is approximately 0.008, and the steady state time step becomes 0.0018. The disturbance goes up, is reflected from the upper wall and goes to the right. The next results. They are the same for the inflow velocity is 1.7 for times 1.3 and 1.8. In the pictures, you can see the density distribution. Alpha is the same. Parameter tau is approximately 0.005, and steady state time step becomes 0.0015. On inflow is not quite a physical condition, so the computational result is not obtained with all alpha coefficients. You can write your questions to chat. And you can find us in Telegram, and you can find us on GitHub according to these references. Also, you can get acquainted with our training tracks with following names: Leap Acoustics, QGDsolvers, a simple FSI training track for OpenFOAM, and implementation of the solver for coupled heat transferred in gas and solid. And now I'd like to thank you, and maybe Andrew will continue.
Hello, dear colleague. We continue our track, and now I will demonstrate how to install and QGDsolvers and how to use it for solving tutorial task. But at the beginning, need to download and install QGDsolver. And as shown in the presentation earlier on the slide number 22, you can find that you may directly download QGDsolver from the GitHub or using git clone command. All commands I post with comments and link to repository. Hello, we have some trouble with internet connection, and now I think that it's all is okay. Hear me?
Yeah, we can hear you. I would advise
Let's
you not.
continue. And
Yeah, I would advise just to share your document and not put your camera on, so it's going to improve probably the connection. Okay. Yeah, perfect. Yeah, start sharing, but don't put your own camera on. It will improve probably the connection.
How to use Git?
Yeah, it's okay. We can see. Thank you.
One comment and. And now the QGDsolver download to my computer. You can try to do this on your PC. After that, we can check that the QGDsolver was downloaded. We see a QGDsolver folder. Now we change directory to QGDsolver, and we must change the branch to OpenFOAM version 2012. It's use the command git checkout digi dev. The branch was changed, and now we can use all we make script to compile the QGDsolver framework. If you took part in our track about QGDFoam in compressible flow simulation using regularized hidden dynamics equation in OpenFOAM, you don't need to download and compile again. While the installation of the QGDsolver is in the progress, I will show a few slides about numerical calculation of trans and supersonic jets and acoustic noise generated by them using the QGDFoam and our libacoustics library. The installation process might take time about 15-12 minutes, and now I will show the presentation with using QGDFoam solver for numerical simulation of transonic and supersonic jets at moderate readiness number. This problem statement, the problem of trans and supersonic jets with the follow initial data were considered. Two tasks were considered. The first is the Mach number was 0.9 and low readiness, and the second is Mach number was 2.1 and the moderate readiness number. For this task we use QGDFoam solver. Schmidt number was equal to 0 in all internal field, and alphaQGD we investigate alphaQGD field in the 0.0 0.05 to 0.3 numbers. Reference paper are available in the on this link. The computational domain in this task was a rectangle parallelepiped in which the output boundary is removed by 100 diameters, and the side boundary it's about 20 diameters. The input boundary, the inlet input boundary, corresponding to the exit of the round nozzle, and coincides this beginning of coordinate system. In additional, the mesh computational mesh has been refined on the 30 diameters to downstream. The numerical simulation was performed using QGDFoam solver. And we use the libacoustics library with Farasat formulation to use to predict acoustic pressure in the far field. These boundary conditions were similar for both cases. In this slide, in this part of slide, you can see instantaneous isosurface of Cook criteria for the low Reynolds number jet. And these graphs show the axial distribution of central line mean Mach number. You can see that alpha QGD equal to 0.50 is a good agreement with experiment data. Also, you can see that the acoustic properties is also have a good agreement with experiment. The schematic Wilhelm-Hawking surface you can see in this picture, S1 and S2. The second case is the moderate Reynolds number. You can see a jet flow velocity distribution. And also you can see axial distribution of central line mean number, Mach number, and also OSPL. In this task, we use Schmidt number equal to 0 in all field, and alpha QGD was 0.15. Our investigation, our results allow to formulate a recommendation for the calculation of a jet at low Reynolds number. The resolution of the grid should be no less than 30-40 cells per diameter. And in this picture, you can see that the potential core length of the moderate Reynolds jet number is between 8-10 diameters. And the sonic point in this jet is reached between 20 diameters downstream. The results show that the acoustic properties of moderate Reynolds jet are closely comparable to experimental data. The highest level of the generate noise occur at angle around 30. At the low Reynolds number, acoustic spectrum is dominated by narrow band of frequencies, and the moderate Reynolds number is at quite full. So we solve this task and validate the QGDFoam solver. And the QGDsolver was performed on the problems on the transonic and supersonic jet. The resolution of the calculated grid should be at least 40 cells per diameter, And the regularization parameters must be Schmidt number equal to 0, and alpha QHD is equal to 0.15. The QHD algorithm, we instigate and compare QHD algorithm with other solvers, and the QHD algorithm makes it possible to correctly model the process of the formation and propagation of the hydrodynamic instabilities at low mesh resolution compared to the, for example, hybrid method for approximation convective terms and the Kurganov-Tadmor scheme. It's a pimple central form solver. But the QGD algorithm is more slower than other solvers. In this slide, you can see reference information. It's the paper. There you can find all information about this task and other parameters for QGDFoam solver and compare with other solvers in the OpenFOAM. Also, you can see a Telegram channel and QGDsolver's GitHub and libacoustics GitHub. Let's return to our tutorial. The process of the compile is running, and we check. You can download the tutorial case. Need to download a test case. It's located in the handouts tab in our room handouts. You can see all our training tracks materials, presentation, and you can find a L channel zip and download this. It is a tutorial case. If you have any question, you can write it in the live question section and discussion forum. Also, all materials are also available in our training tracks repository, and it is need to download. It's need to download L channel zip from the handouts, and it is the fastest way. We can check. I have already L channel case, and let's check all parameters in this case and compare this presentation. It's a velocity field. You can find that the Mach number equal to 1.2. It's equivalent to Mach number. And Marie has already considered the formulation of the problem of a flow in L-shaped channel and the initial and boundary condition. It's was presented on the 25 slide number 25. Once again, I would like to remind how QGDFoam differs from the other solvers. It is a presence of regularized parameters, which are calculated in the solver using the alphaQGD and Schmidt alphaQGD and Schmidt-QGD fields. You also need to specify how the Schmidt number is calculated in the thermophysical properties. If you see in this section, we must see that the QGD coefs set as a constant. So it means that the Schmidt QGD number is defined by constant equal to 1 in all fields. Also, you can check this in the Schmidt QGD field. It's internal field 1, and the other boundary condition sets the fixed value to 1. And alphaQGD field is set to 0.05 in all field. We can check that we use implicit diffusion is true, and turbulence model is laminar. We don't use the turbulence model. And if we check control dict file, we set the max current number is set to 0.2, and end time is 4:05. Let's check our the solver compiling now. It's so slow. Do you have any question about the download QGDFoam solvers or installation or compile the? Please write any question to chat, and we try to help you to download or compile the QGDFoam solvers. Now libqgd library compiled successfully, and now the compile the QGDFoam solver. After the compilation compiled has been QGDFoam has been compiled, we try to start our case and see the result in the paraview. So we go to the L channel case. We check them, and now we make block mesh command to make mesh in the in our case. After that, it's check mesh. Check mesh, and mesh is okay. And we run the QGDFoam, where calculation is starting, and the calculation takes about 2-3 minutes, and we can see results. We have any problem with internet connection? No, all is okay now. Let's start ParaView. The calculation was is finished, and let's see the result in the ParaView. Не работает. For example, we see the pressure field. And for example, is the U field. You can see how the gas flows upwards to the top wall, and it's reflect from it and turn right. Let's try to simulate different Mach number and set the Mach number equal to 1.7. All we clean, set to 1.7. Set to end time equal to 3.5, and make mesh, this block mesh command, and start the QGDFoam. The QGDFoam is calculating. Then the simulation we see the result in the ParaView. Let's see the result. and the pressure. So let's try to change our mesh and set the resolution more resolution mesh. We must go to the block mesh dict file and set a different mesh resolution. For example, we use not 50 points, use 18. And check our mesh. Our internet connection is not good. We make mesh with block mesh. Mesh is check the mesh. The mesh is okay, and run the QGDFoam solver. The simulation starting, and then we can try to use different regularized parameters to change after this simulation. We change the alphaQGD field and compare the results. I repeat that if you have any question, please write it in the question section. We have no question. The download. The QGDFoam is more have more time compare this other solvers, but it's there is less mesh resolution for this result. I think that we must see the result of the new mesh. The shock wave capture on this mesh more and velocity field. For example, let's compare the two results with different alphaQGD field. Stop this calculation and make all the clean, and make two folders. One is the L channel with alphaQGD 0.5 and the two 0.3. For example, let's check alphaQGD field, yes, and make all run script. Let's takes 2-3 minutes to calculate this task. And then we change the alphaQGD field. Copy some. Let's wait 2 minutes to calculation. So mesh, we have a mesh resolution, and try to modeling with other alpha. For example, for 2, let's see the result. The flows reflect from the top wall and turn right and wait a few minutes and to continue. Let's stop this calculation. I think it's this time is enough. Copy case to the new folder and change alphaQGD field to 0.3. And also run the all run script. It's the alphaQGD 0.5 and Schmidt QGD equal to 1. Let's wait wait a few minutes and see the result from the other alphaQGD field. Let's compare two results. For example, on the time equal to 2 seconds, white. You can see that the shock wave it's more clearly in this with alpha in the, and this is not as a physical solution. So it's all. And in conclusion of the training track, I would like to say that we have a Telegram channel. It's you can see in the contact slide. We have a Telegram channel dedicated to the use of a solver based on QGD equation, and a repository of this QGD framework and other materials of the course conduct for the OpenFOAM workshops. For example, it's a lib acoustics library. I will duplicate this information in the discussed forum for your conventions. It's if you have any question, please write, and we have a few minutes to answer your questions. Also, you can find all our materials in handouts section. This is their presentation, test case, and other support materials. With no questions, I think that we may end our training tracks. Thank you very much for your attention. I think that it's some interesting for you to use a new QGDFoam solver to compressible to use in the compressible flow simulation. Thank you very much. That's all. Thank you.